Hi everyone. In this video, we'll be controlling the brightness of a single LED using a microcontroller. Our microcontroller is our reference good old PIC10F220, and we have a very simple circuit, which is just a good old blinky circuit basically. We have the 220 ohm resistor connected to the GP0 pin of our microcontroller. We have the LED, we have the PIC tree to program and power the circuit. And that's pretty much it really. To do this, we will generate the digital signal with a technique called PWM. PWM stands for pulse width modulation. In simple terms, modulation means expressing any kind of data on some sort of carrier signal. So our PWM signal will be a digital signal. You might also hear terms like pulse signal, square wave, pulse train. So a PWM signal has a frequency and period, just like any other signal you have, and it has another attribute called the duty cycle. A pulse width modulated signal has an on and an off state. On state is where we have the pulse and the signal is high, and off state is where the signal is low. So duty cycle is expressed in percentages, and it's the proportion of the duration of our on signal to the period of the entire signal. So let's try to generate a sample PWM signal. The target period that we have will be 100 microseconds, and our frequency will be 10 kilohertz, and we are aiming for 10% duty cycle. To achieve that, we need to spend 10 microseconds on the on state, and we need to spend 90 microseconds on the off state. So let's jump into the code and see how we can do that. Is to set our GP0 pin to on state first and delay for 10 microseconds and turn off the GP0 and another delay for 90 microseconds. So in the loop, we have a total of 100 microseconds. That will be the period of our signal, and our signal will be on for 10 microseconds and it will be off for 90 microseconds. That would give us a 10% duty cycle. So let's program this and see what happens. Now, if you look at our LED, it's not as bright as it was anymore, and we are generating a PWM signal with 10% duty cycle at 10 kilohertz. Now let's check our signal on our scope. So as you can see, let's put some cursors in there. That's the beginning of it. And yeah, if you check our parameters here, we have like about 100 microseconds of period, and our signal is about 8 kilohertz, which is close enough for the 10 kilohertz that we were heading for. Now, one common way of generating those signals is using a timer module instead of these delays. So let's have a quick refresher on the timer module from our datasheet. The timer module on our microcontroller PIC10F220 is an 8-bit timer / counter. It increments with every instruction cycle. If you are curious about instruction cycles and clock cycles, check my previous video, link down below. So if you configure timer 0 module as timer, it will increment at every instruction cycle of the microcontroller. And since it's 8 bits, as soon as it reaches 255, it will overflow and go back to 0, and we will do the same thing again. At 8 megahertz internal clock, we know that the instruction cycle is 500 nanoseconds. So let's do a quick calculation here. If our instruction cycle is 500 nanoseconds, which is 0.5 microseconds, and our timer is 8 bits, therefore it needs 256 times to overflow, then what we are looking at is 128 microseconds for our timer to overflow. So we will read the same value at TMR0 register at every 128 microseconds. And that is, if we divide it to 1 million microseconds, which is a 1 second, to calculate the frequency, we will find 7,800, like 7.8 kilohertz really, of a signal that we can generate with our timer in its fastest mode. So we don't need to go as fast, because when you're driving an LED, there's this thing called persistence of vision. And as long as it's just like your monitors and LCDs and other display stuff, as long as you are over 100 hertz, generally your eyes won't be able to see the flicker on our signal on the LED. So let's try to configure our timer. There are a couple of things with this PIC. So our timer has also a prescaler, which we can use to increment its period. So, and the prescaler is configured by the option register bits. And if you look at the prescaler rate select bits, so we have 2 to 256. And there are a couple of other bits that are important. We need to assign this prescaler to timer 0, because in this PIC, you can't assign it to, you should assign it to either timer 0 or watchdog timer. We won't be using watchdog timer for simplicity, so we need to assign a prescaler to the timer. And we also need to enable our timer with the clock source. And we will use the internal instruction cycle clock to set it as a timer, otherwise it will be a counter. So let's go over the same calculation, this time with a prescaler. So we said that our instruction cycles are 0.5 microseconds. It takes 256 instruction cycles for the timer to overflow. And if we apply a prescaler, let's say something like 64, then we are looking at 8 milliseconds. If we divide 1 million microseconds to 8,192 microseconds, we will find our frequency, which will put us at something like 122 Hertz. And that frequency is high enough to drive an LED. So I'm just going to assign a bit literal to our option register so we can see. The first 2 bits aren't important. The 5th bit is to set our timer as a timer rather than a counter. And the next bit isn't important. And we will be assigning our prescaler to our timer. And I will be setting our timer prescaler as 64, which is 101. If we check our datasheet again, to achieve a timer rate of 64 in the prescaler, just last 3 bits had to be 101, which is what we did in the code. Okay, so based on our configuration of the timer and our clock frequency, so our instruction cycles will take 0.5 microseconds. Our timer is an 8-bit timer, so it will take 256 instruction cycles for it to come back to overflow and come back to its original value. And we set the prescaler as 64. And that means it would take our timer 8,192 microseconds to overflow. And that would give us roughly 122 Hertz. So to replace those delays, we know that our timer value will change between 0 and 255. What we can do here, instead of using these delays, we can assign our GP0 to timer 0 less than 25, and that will just roughly give us a 10% duty cycle. Okay, let's have a look at our LED first. There's a bit of flicker that could be seen on the camera. We can maybe make it a little bit faster, but it still looks like quite dim. And now let's check our scope to see what kind of signal we have. Let's set our divs to 5 milliseconds. And let's adjust our cursors to see what's going on here. Okay, so if you look at it, we have like roughly 10 milliseconds, about 10 milliseconds of a period. And we have like roughly 108 Hertz, that's close enough. If you look at the on time of our signal, it's about 1 millisecond. If you look at the entire signal, it's about 9, so it's close enough here. Our signal is close to 10% duty cycle. So I'm going to leave it there and define some variables. First, we have our duty, which is, we can just start it from 0. And I'm going to define a duty delta variable, which we can initialize at 1. And now we also need, in addition to the timer, we need another counter that would change our duty. So just call it animation counter. I will put it 0 for now. So instead of the fixed value of 25, we will put our duty here. And now we will increase our animation counter. And I'm just eyeballing the animation time here a little bit, but what we can do is whenever animation counter is 4, this is an arbitrary number. You can adjust the animation timings more closely, looking at the instructions that I've generated. We will increment the duty with our duty delta. So what will happen here is that our duty cycle will start from 0, and every time our animation counter reaches 4, it will increase our duty. Just need to clear our animation counter here too. So our duty will keep increasing, and since it's an 8-bit variable, it will increase until 255, and then it will go back to 0. So let's program our device and see what's going on. Okay, now if you look at our LED, it's flickering really fast, so apparently our animation counter needs to be much slower than this. So let's put something bigger here, like 200. Again, complete eyeballing this. Okay, so let's have a look at our LED. Our LED is glowing from 0 to 100% duty cycle and jumping right back to 0 right after that. So we want to animate a little bit better. Let's have a look at our scope to see what's going on with the signal. Again, we have the same 100 Hertz, close to 100 Hertz frequency. And if you look at our duty cycle, it's changing from 0 to 100, close to 100, and then it's jumping back. So we want it to travel back and forth, like from 10%, from 0%, go to 100%, and come back slowly from 100% back to 0 instead of just jumping right back into 0 from 100%. So to do that, we just need to check for the boundaries of our duty. And in this case, given it's an 8-bit variable, it's either 0 or 255. And what we're going to do here is, when this is the case, we will just negate our duty delta. So if it's going in the positive direction, it will go in the negative direction. If it's going in the negative direction, it will go in the positive direction. So yeah, let's put that in there. Yeah, and then once this happens, once we change its sign, we just want to add it back again onto our duty so it doesn't get stuck from in these boundaries. Yep. Okay, so that should do it. We can even make our animation a little bit slower. We can say 255 here, or even 0 will be fine because our animation counter will also overflow. So let's program this and see what's going on. Okay, so let's have a look at our LED first. Yeah, that's exactly what we were looking for. If you want to adjust the speed a little bit, you can just change the if statement where we control the animation counter from 0 to something smaller than 255. Like, let's make it faster. Let's put it like 220. I'm just eyeballing it, complete arbitrary numbers. But yeah, basically this is going to be adjusting our speed. Or you can just adjust the oscillator frequency here. There's like a lot of ways to do this. This is just an example how we can use the timer to generate pulse width modulated signals and drive the LED. I will also link the code in the video so you can check out and play with it yourself. Yeah, we programmed this. Let's have another look at our LED. Yeah, it's sort of kind of faster now, and let's see what's going on our scope. If you look at our signal, yeah, now we can see that our duty is changing from 0 to 100, slightly closer to 100. We have some sort of dead band here, but that's fine. That's good enough for this. And yeah, it's traveling between 0 and 100% and back and forth. So that's pretty much it. Let me know if you have any questions, comments, and don't forget to have fun and stay hydrated. See you later. Bye.